Okay, let me show you another application of the algorithm embedded in section 4.4. This section was about unbounded returns, and if you remember, the algorithm is about finding an upper bound for the value function, for the to be more specific, for the supremum function, and starting the iteration from that upper bound with the Bellman operator. We will find, in the end, we will find the value function. So in this exercise, we have a firm, and this is the objective function where x stands for period t capital stock and y stands for next period capital stock. So we need to find an upper bound for the value function. So first we need to find an upper bound for the one period return function, and given the negativity of this parameter, if 1 equals x, this whole part of the expression is cancelled, and the remaining part is this. Where is the maximum of this expression? But before asking this question about the maximum, it is questionable whether it has a maximum at all. So we can simplify the expression in this way, and we have this solution. So when x is a over b, and given the fact that the second derivative is negative, the one period return function has a maximum at a1 over b. But we need the maximum value of this function at x a over b. So let's put this value into the remaining part of the function to get to, through a few steps, to get to this expression, which is the upper bound for the one period return function. So this is an upper bound for the one period return function. As one period returns cannot be higher than this expression, we can have an upper bound for the value function on this basis. So we have this expression. This is the maximum problem of the firm, and it's lower than this expression. So we're gonna use the upper bound for the one period return function. It can be traced back, it can be reduced to an infinite sum. Which is this expression. So here we go. This is a useful upper bound for the value function. And so we can say we have this upper bound. So at this point, from this value function, we can start the iteration with the Bellman, the usual Bellman operator. Just to be on the safe side, we can check, and actually we are supposed to check, if the assumptions of Theorem 4.14 hold. So the operator must be decreasing. So actually we have 3 assumptions, and all of the assumptions hold, trust me. Let's start the iteration. So at this point we can start the iteration, the repeated use of the Bellman operator, to see where we go. So we have the one period return function in the Bellman equation. So when we say let's start iterating with the Bellman operator, it means that we start using the Bellman equation to receive further and further approximations for the value function. Our decision variable or control variable is next period capital stock, y. So we need to derivate the Bellman equation with respect to y, and this is the first order condition we have. Which means we have a very simple policy function. In the first round of iteration, this is the optimum policy. So let me emphasize, this is not the optimum policy function. This is the optimum policy in the first round of iteration. It may change, and it will change. So at this stage we know it may change. After the first round of iteration, we want to have the value function, the outcome of the iteration, in a closed form. And this is what we have. So after putting the optimum policy function into the Bellman equation, we have the outcome of the first round of the iteration as the value function. And okay, it's not necessary to write it down again. So let's have the second round of iteration. So we write down the Bellman equation with the value function in the second part as the value function we received in the previous round. So this is the one period return function, and here comes the value function of the previous round, evaluated at next period's optimum capital stock. Next period capital stock. Actually, we are trying to find the optimum value. So to be clearer, this is what we have. So this is the value function. We are iterating, and we use repeatedly the value function of the previous round. So again, we need the first order condition with respect to y, the control or decision variable. So we need to derivate this expression with respect to y, and this is what we have. And we can solve it. We can solve it for y. We can solve it for y. So after the second round, this is the optimal policy function. Okay, and we can see that it has changed. So while after the first round it was the optimum policy function, after the second round this is the optimum policy function. One thing didn't change, one thing hasn't changed. We have linear functions, so you can see that the optimum policy function is still a linear function of the state. So before moving on, we need to put in an explicit form the value function of the second round. So it's gonna be long, and this is the main difficulty of the exercise. It's relatively simple to solve. The idea is simple, but it's very easy to miscalculate. So you must be very careful when solving this equation. I won't do all the steps, it's not necessary. You can practice, you can do it instead of me or with me. So now I am writing down the first row. Of putting the optimum policy function into the Bellman equation of the second round. It's relatively short, but it's longer than it was, and it's easy to get, it's relatively easy to get to this value function, which is the outcome of the second round of iterating. This is ugly. Iterating with the Bellman equation, with the Bellman operator. I think it's correct. Let me double check. Oh geez, I think it's fine. At first it looks nice. So far so good. Yep. It continues. Yes, yes. And here we go. the fun thing is that I tried. So initially, I thought it was going to simpler and easier to solve the problem in MATLAB. So if you have the symbolic toolkit in MATLAB, you have a very powerful instrument to work with symbolic expressions like this, but I failed. So it's still easier to solve this problem with paper and pencil. So we have this value function. So this is the outcome of the second round of iteration with the Bellman operator. Hopefully it's correct. I think it is. I'm just double checking again to avoid mistakes which may confuse you. So let's have the third round of iteration, which is maximizing the Bellman equation with respect to y. Okay, I am writing down the problem. So this was the easy part because this was the one period return function. And here comes the difficult part because here we need to put the value function of the previous round into the Bellman equation evaluated at y. I think it's correct. Yeah. It takes some lines. Okay. Okay. And I think we have the last part of the expression. It's terrifying. Yes. And the last bracket. The first order condition is still comes from derivating the Bellman equation with respect to y. And let me show you what I have. There is some good news in this first order condition. Namely, we only have first order expressions in y. So there is no quadratic forms, expressions I mean. Oh geez. Delta squared by minus 2 delta ab. Yes. and it equals 0. So this is the first order condition, and it takes some time. I don't want to place all this on you because for me it took some hours to get to the end result, but finally, so if you have, and I think you should do this, you will get to this policy function. I need more space, so I need to rewrite. This is fancy because what we see is a recursive formula for the parameters. Okay, so this is the third. This is the policy function after the third round of iteration. It is still linear in X, so the policy, the optimum policy, is still a linear function of the state. But here and here, these are recursive formulas for the parameters of the optimum policy function. And from this optimum policy function, we can have this recursive formula for beta and alpha. So we could proceed, and we would experience that the parameters of the policy function change in each step. But we have two nonlinear difference equations for the parameters, and that's all. So this is the solution, and I suggest you should go over the whole process. It takes an hour or two, but trust me, it pays. It improves your accuracy and your mental endurance. So this is an exercise not only in mathematics, but in mental endurance. All right, so that's all for now. And in the next seminar, in the third seminar session, we are going to meet the optimal linear regulator. Bye-bye.